So let's talk about vacuum systems. I want to talk about where we use them, how they work, and how we can actually calculate the correct vacuum pad, whatever a vacuum pad is. Yeah. So we'll talk about, actually I'll demonstrate some vacuum stuff. I have a little vacuum pump here that I'm going to use, and I want to demonstrate kind of how the seal is so very important, and also how the diameter of the vacuum cup, or the area that the vacuum is applied to, is so incredibly important. Okay, so let's move forward. So here we go. This is vacuum pads, and this is what's, they're used all over the place. Okay, essentially vacuum suction cups pick stuff up, right? So vacuum suction cups are used in all different kinds of manufacturing industries and packaging, and it goes on and on and on. If you need to pick anything up, like without actually grabbing onto it, you just suck it up, then use a vacuum system for sure. Okay, so vacuum systems are used for, they're all over the place. This is a really cool situation. I like this one because it helps to kind of paint the picture of porosity, or more specifically of the connection or the vacuum seal itself. Now take a look at this. These guys are pretty big. See that little vacuum pad there? That's pretty big. It's a lot small. It's a lot larger than these little tiny guys, but these little tiny guys are connecting onto this really super smooth surface. So if we go down here, this vacuum pad is really very large. What's going on there is that we need that because this guy is porous, plus it's quite flexible. Okay, I'll cut that out. Good morning, Amy.
Morning.
Sorry, I'm doing a video. I apologize. Is that okay?
No, it's fine.
Okay, bye. And we can see there are 6 of them here to kind of stabilize it, because that's a thin piece of plywood. But it's really large because the vacuum seal isn't going to be very good on just a piece of wood. Okay, so here we go. Here's another piece of wood. Now this is laminated wood. So these guys are still pretty big, but this thing's really heavy. I mean, here, these guys have to be the same size as these guys because the porosity. So the vacuum seal, it really sucks on a piece of plywood, but on laminated wood is a really good seal because it's such a flat surface. Here we go. Now these are bellowed vacuum cups, and they're for picking stuff up that's kind of on an angle or a bit of a curve to it, or maybe something that's not perfectly flat. We want to use a bellowed cup. It kind of forms to the different shape. Here we go. Here's just an application here. You can see all these little kind of vacuum cups that are going on here. They're picking up the tops of cans and they're placing onto the vacuum. So that with a vacuum, they're placing them onto paint cans. Here we go. Now this is pretty cool. Now there's a whole bunch of vacuum pads in this picker-upper, right? So this robotic end is picking up these boxes. Now cardboard, the porosity of cardboard is air can kind of go through it, and the seal there is not very good. So this whole rail has vacuum cups in it. There's a lot of surface area, so we're actually able to pick up things like boxes and stuff. It's pretty cool. So what I want to do is, that's kind of, that's where we use vacuums. Pretty much we're going to focus on vacuums in industry. And what I want to do is I want to talk about what a vacuum is and where do we find vacuums. Okay, so a vacuum exists only because of the atmosphere around. Okay, so we cannot have vacuum without atmosphere. So the only place that vacuum exists truly without atmosphere is space. But then again, there's actually no vacuum in space. Really? Well, space is a vacuum, but there's no vacuum there. That comment will start to make a little bit more sense as we go on. We can't use the vacuum of space to do work for us. We need the atmosphere to do work. So although space is a vacuum, we can't use it. Okay? So how do we measure vacuum? The maximum possible vacuum is whatever the maximum possible atmosphere is. So essentially, vacuum, the work we do with vacuum is actually, just the atmosphere picking stuff up. Really, truly, it's the pressure differential makes a force differential. So we have this atmosphere all around us, and we know that it has a particular pressure. Well, that pressure can be used to apply force. You know that, right? That's not a biggie, right? So if we were to use a vacuum to decrease the pressure on one side of something, and we knew that there was pressure on the other side of something, well, there's a force there, and that force actually sucks, pushes, I think pushes is the better word. The force is actually pushing whatever product is up against the vacuum pad. And then they're like really connected. They're connected so much that you can physically pick something up. Yeah, it's pretty cool. So how do we measure vacuum? I don't know. I guess we'll get into that. Okay, good. So what's going on here is that vacuum is really relative to atmosphere, and we know that the atmosphere changes as we go up, but as we're down at the bottom, like on the surface of the earth, our atmosphere is 14.7 psi. And from there, we can actually apply 14.7 pounds per square inch of force to connect something to a vacuum. And this is a vacuum. There's like nothing there. Actually, there are actually some molecules in space, which is pretty cool. There's actually a pressure, air pressure in space. Air pressure is the wrong word. There are like some hydrogen molecules, actually a lot of hydrogen molecules floating around in space, but they're so like dispersed, right? That they're just whatever. There's the vacuum, the pressure there is really low. It's actually not zero, which is really weird. But if we take a look at these numbers, like there's actually this extraordinarily low pressure in space here, and then way out by the moon, it's really even lower. But we use, as we know, all of the pressure that we look at for absolute pressure is relative to space. Space is, we consider a vacuum. Yes, but we can't use it as a vacuum. Okay, let's just move on. Okay, so what's going on is that we need to be able to measure vacuum, okay? So, and we know that the vacuum has to do with the atmosphere. The usable vacuum here on Earth has to do with the atmosphere. For instance, if you had a vacuum machine, same vacuum machine would do less work if you took it up a mountain. Yeah, because the atmospheric pressure is less, okay? So it's the difference between, or the differential pressure between the atmospheric pressure and the removal of the atmospheric pressure. Yeah, I think that's kind of a good idea. Now, we don't have to get into Torricelli, because actually go look up Torricelli, like go watch the history of Torricelli. It's awesome, the stuff that was going on with this man. Brilliant man. So, but he made this tube that actually measures vacuum. I don't need you guys to know that specifically. It's just that it's really cool. This is like a scientific thing. So, but there's this term that you kind of gotta get out of this, and that we can actually hold this vacuum can hold up, the air pressure can hold up, or the vacuum can suck up. Well, I guess we could look at it two ways. Actually, 30 millimeters of mercury. Well, almost 30 millimeters of mercury. It's pretty cool. So when you hear pressure measured in mercury, or vacuum measured in mercury, it's actually a form of measuring pressure. We have PSI, we have newtons, and we have millimeters of mercury. We have inches of water, lots of cool stuff. But essentially what's going on here is the atmospheric pressure is pushing down here and holding up mercury. Mercury's super crazy heavy. We can hold up almost 30 inches. I said millimeters, I lied to you. I meant inches of mercury. Yeah, pretty cool. So let's move on here. And we've got, this is just another concept. That's cool. Like, you know, the whole vacuum thing with the Torricelli tube is really cool. Let's just take a look at some units. We can look at inches of mercury, inches of water, or feet of water. Sometimes that's used. PSI. So let's just stick with PSI because we're used to using PSI. So we're just going to go through and use PSI as we look at our vacuum systems. Now, I need to talk about negative numbers. Okay, so essentially, I need you to think of atmospheric pressure. Okay, so you know it's 14.7 psi. Right? Relative to space, it's 14.7 psi more than space. So relative to space, it's 14.7 psi. It's more. Okay, that's fine. So a vacuum, if we said, hey, what's a vacuum of 2 psi? Well, 2 psi is actually way below atmospheric pressure. It's 2 psi up from space. Okay, so the difference, if I created a space, okay, if I put, like, I don't know, here I have a vessel, pretend vessel. There's a vessel, and there's 2 psi in there. There's a lot less air pressure than there is out here. So the difference between the two is 12.7 psi. Okay, so there's actually 12.7 psi of pressure creating force to push that thing together. So we've got this difference. I want to kind of look at how we look at vacuum. Okay, so if I were to study the air in there at 2 psi A, and I know this is 14.7 psi A, what's the vacuum value of that? Now remember, vacuum is relative to this stuff here. We can't work with vacuum unless we have this. It's the differential pressure. So the differential pressure is actually the pressure creating the force. So when we look at vacuum, we measure vacuum in two different ways. One is psi A, the absolute vacuum. Okay, so that's 2 psi in this magical little ball here. But psi A, sorry, it's 2 psi A in this magical ball. What's the psi G in here? What is it? Well, it's actually, if you think about it, that's the work we're going to do. The psi G, the gauge pressure in there, is actually minus 12.7 psi. Just psi or psi G. Okay, so it's, when we're looking at vacuum, we can actually look at it two ways. But ultimately, when we're doing math with vacuum, when we want to know how much force there is, we need the differential pressure. So we're looking for that negative number. How much it is below atmospheric pressure. What's the difference between the pressure in this and the atmospheric pressure? So actually, essentially, it's going to be a negative number that we're going to look at that actually does the work. Now, I know this is weird, but we're looking at the differential pressure. That's the actual stuff that does the force. So even though it has a negative number, we don't put the negative into the formula. I'll show you that in a minute. But here we go. Let's just go to this slide. Essentially, we've got these different values here, and these are all negative, okay? There's another way of looking at it, 0, okay? So a perfect vacuum is 0 psi A, okay? So, but if we go up from a perfect vacuum, this is a perfect vacuum here, we can go up here, and we can look at this. It's 9, now I got an example here, 9.7 psi A. So if I had a vacuum that was minus 5, and that means minus 5 from atmosphere. It's 5 less than atmosphere. What's the absolute pressure? Well, it's 9.7 psi A, absolute pressure. So often we may be given pressure in negative numbers because, given vacuum in negative numbers, because that's the number that's actually going to be doing the work. That's the number we use to calculate work. But sometimes you're given pressure in absolute values. And then you have to figure out how much below that is from 14.7, which is the absolute value of the atmosphere. Okay, good. So there we go. So let's just move on here and take a look at an example. Let's look at the math in play. Now, this is cool. I'm creating an atmosphere that isn't on Earth. Okay, so this is in the space station. Okay, so the space station has an atmosphere in it, and it's pressurized. Okay, so what's the pressure in the atmosphere in this space station? Well, we want to actually calculate that because we've been given a bunch of information, and we know that there's a formula where we look at absolute pressure, atmospheric pressure, and actually the gauge pressure itself. So let's take a look at this. The reading on a gauge, okay, is connected to a vacuum tank is minus 6.7 psi. So that means it's minus 6.7 less than the atmosphere, whatever the atmosphere is. I mean, we're not on Earth. It's not 14.7, or it could be, but I'm guessing that it's not. Okay, so the gauge says it's minus 7.6 psi, so it's below. So there's definitely a differential pressure there of 6.7 psi. Okay, so if I want to do the math to calculate the actual absolute pressure in there, I need the atmospheric pressure. So if I'm going to take a look at this, so I'm looking at the atmospheric pressure. If I was on Earth, okay, and I was taking a look at this gauge, and it said minus 7.6, and I know the atmospheric pressure is 14.7, then I could calculate actually the absolute pressure. I could see what that vacuum is in absolute pressure, and it's going to be 7.1 psi A. So I've got this tank. Inside it is 7.1 psi A. What does the gauge read if it's in 14.7 psi atmosphere? It's just the difference between 14.7 and 7.1, because those are both absolute pressures. So that difference is the number I want to use, and that's going to be the gauge pressure. That's going to be what because again, remember, gauges tell you the differential pressure between what's inside a vessel and what's in the atmosphere. So that differential pressure is the stuff we do the work with. Good. So here we go. Now, different situation. We've got a space station, okay? And we can see that the engineers have designed a vacuum system where absolute pressure of 14.9 psi, okay, that's obviously going to be a vacuum because I'm imagining the atmosphere in this space station is greater than that. It's got to be close to 14.7 psi. Is required to drive a vacuum actuator locking a door mechanism in the International Space Station. Okay, cool. The system is working well as you perform your system diagnostic. Okay, as you take some readings, you record that the vacuum gauge, remember the engineers designed it to be working at 14.9 psi. Okay. It does, and the system's working well. Okay, so you know that the vacuum in there is 4.9 psi. And you go and look at a gauge, and you see the gauge is reading minus 10.1. Okay. That's good. So you know the vacuum in psi A, the vacuum in that tank in psi A, and you know psi G. You're good. Okay, so that's good. Okay, so everything's working great. Okay, what is the atmospheric pressure in the space station? Well, to calculate atmospheric pressure, we need gauge pressure, right? Whether it's a vacuum or a pressure. We need gauge pressure. We need absolute pressure, and we need the atmospheric pressure. Well, we've got the gauge pressure. We have the atmosphere. We have the absolute pressure. So let's calculate the atmospheric pressure. So we just throw that into our formula. We know our absolute pressure, and we know our gauge pressure. We'll put it together. It's minus a minus, so that's plus, right? Okay, so it's 15 psi. That's 15 psi A. That should actually say psi A. I'm going to change that. I'm going to do that right now. Whoa, how do we do that? What do I do? What happens? I'll change that later. Okay, I don't want to screw up my PowerPoint right now. Let's move forward. Okay, good. So this is cool. This is the conclusion here. And 14 psi A, or 101 kilopascals, which is another way, Pascal is another way of measuring pressure, and also inches of mercury. Okay, good. So there's no way to make this vacuum any larger than that. A vacuum is the difference between the pressure outside a vessel and inside a vessel. More specifically, the pressure inside a vessel is less than the atmospheric pressure, creating a differential, creating a force. Cool. So, and then the other thing is that the supply lines must be appropriate sized. Okay, they can't be too long. If they're really, really long, that actually creates problems for vacuums. And they have to be specialized kind of vacuum lines because they get sucked in, right? So you have to get special vacuum lines. Okay, good. So as far as the vacuums go, there are different kinds of vacuums, or vacuum generators, or vacuum pumps maybe. More specifically, let's just call them generators. Okay, so vacuum generators come in Venturi, reciprocating, and rotary. Now, I've got a reciprocating here on my bench. I'll show you that in a minute. Venturi is a really cool thing. We're going to study that because it's a very common type of vacuum generator. Now, there's also a rotary vane and a rotary screw. Okay, these are common things as well. We're going to focus on Venturis, and I'm going to demonstrate my reciprocal. Okay, rotary vanes and screws have very high vacuum rates. Any rotary kind of compressor or vacuum generator, essentially they're doing the same thing. They're just uncompressing gas, right? So any kind of rotary will have high flow rate, but maybe low pressure. And the reason we may need high flow rate is because we have a really poor seal. There's not a good seal. Vacuum's all about giving a really good seal, and I'm going to demonstrate that momentarily. Okay, good. So reciprocating, we've got pistons and diaphragms. I've actually got a combination here. My pump is a piston with a diaphragm in it, which is pretty cool. But I've also got diaphragm pumps as well. And then there's a Venturi. I'm going to demonstrate to you the reciprocating one, and in doing so, we will see how the flow rate and the seal are very important. In that if we have really high flow rate but a poor seal, sometimes that's okay. But if it's a really low flow rate, we need a really good seal. And reciprocating pumps have low flow rates, so they need really good seals. Often when we have a poor seal, because we're trying to pick up cardboard, or we're trying to pick up something that's really porous, often we need a really, like we need a vacuum cleaner, like sucking up vacuum cleaner. Now, actually, vacuum cleaners, as you probably know, are reciprocating. Pretty cool. So let's move forward and take a look at an example of a reciprocating vacuum, and we will study seal, and we'll study we'll look how flow rate helps with seal, and then I'll jump in and I'll actually show you guys Venturi. I don't have one here, but we can go through what they look like. All right, here we are looking at a reciprocal vacuum pump. Actually, it's pretty cool. This thing here actually is a pressure pump as well. So it sucks air in here and it blows air out here. So I'm using it as a vacuum pump. It's actually designed to be a vacuum pump, but it's also just a compressor as well. Okay, good. So what I've got is, I'm going to turn it on. You can hear it reciprocating. It's a 12-volt DC pump. And I've got a seal in here, okay? So now, you can hear it working a little harder. And I can feel that connection to my finger for sure. So there's definitely a force. There's a force between my finger and this. And that's because of the atmosphere pushing my finger onto this tube. Now what I want to do is I want to do some work with this thing. Now, one of the things about vacuums is the larger the surface area here, the more work you can do with it, because pressure and force and area, they're all connected, and we know that the larger the area with the same pressure, we can create more force. The same exists with vacuum. When we have a greater area, surface area, we can actually create a greater differential, force differential. So here we go. So what I'm going to do here is I've just got these little guys here, and I'm going to pick up some stuff. I've got some paper. Now, if I had something that was a really good seal, I could pick up heavier stuff than just this paper. This stuff is really shiny. It's a really shiny paper, and it's got a really flat surface to it. So as I do this, it's strong. Hear that vacuum? Hear the pump working? It's strong enough to pick this up. So that's a pretty good connection. Over here, this is a little bit more porous, but not a whole heck of a lot more porous. Let me pick it up on this side, see if I can do it. I can pick that guy up, and he's okay. Now, this material is cardstock. It's a little bit more porous. The material is not as good a connection. So as I do this, it's harder to get a better seal. There, I think I got one. No, I can't pick it up. I can barely pick it up. Oh, I just did pick it up. Let's see if I can do this and kind of press it on here to get a really good seal. And now let's see if I can pick it up. I can just barely pick it up. So really, this porosity, there you go, I've got something going on. Even though this guy, I can pick that up a lot easier. This guy, even though it is a little heavier, the seal is so very important. Now, same with this guy. This surface is a little flatter than this. This one is more difficult to pick up. This guy's really big. Let's try this guy. Oh, I got that one. Oh, it doesn't hold on very well. Again, if I did this, I think I might be able to get it. It's barely holding on because it's porous. Now, what I'm going to do is I'm going to crease the surface area here. So I'm going to take this guy. I just kind of threw these tubes together. The seals aren't perfect, but that's okay. That's why we have a flow rate. If I were to take this vacuum and make it, say, with my mouth, just suck on this tube, suck on this tube, we'll turn that off. And if I were to do this, okay, wait a second, I do this, what is that? No. Now, what I'm doing is I'm sucking on this, creating a vacuum, and then I'm just blocking it with my tongue. So there's no more flow, and this thing just falls off. And that's because it's not a good connection. Now let me just get this guy. Let me try this guy. Let me see what's going to happen if I do that here. It's a really good connection here. It's falling, and I think it's because there's air leaking through here. Let's just try this. This is maybe a better connection. there's air leaking from there. Because there's air leaking, I have to keep sucking to hold on to it. So that's why airflow is so very important. We need a lot of airflow, especially if there's a really poor seal. If there's an excellent seal, we can actually use no flow at all. But that's not how vacuum systems work. We work on the fact it's an excellent seal. Actually, you have seen vacuum systems that don't continuously suck, and those are those cool vacuum cup things that you put on glass that you can pick panes of glass up with you, and you create the vacuum and you pick it and it stays there because there's no leaking. So when there's more leaking, we need flow all the time, and that's sometimes why we may use a rotary vacuum generator, because it's leaking all the time. So moving forward, let's actually look at surface area. What I'm going to do is I'm going to put this guy back on here, and I'm going to hook up this other tube to it. Even though I've got a leaking tube here, it's okay because I have a flow rate. I can handle that. Now, what I'm going to do is I'm going to try and pick this guy up. Now, the surface area is larger, but this is not cut perfectly flat. If it was, it would be better. So the geometry of what this looks like is so very important. Okay, that's not even holding on to that. Let me just put this on here. I'm going to create a really good seal. I'm going to push onto it. Now there's that seal. Now, because it's a good seal, it can really hold on to it. If I tried that with this, because the surface area is much different, I can't even hold on to it anymore. No, I can't hold on to it anymore. I picked it up before, didn't I? Well, stop that. There we go. See, it fell off. So, because I've got a larger surface area, I'm creating more force. Okay, so now let's go up one more, and I'll show you something really cool. First of all, my finger skin is a really good seal, as you know, right? So I'm going to do that. I can really feel that. Now let me just see if it'll hold the weight of the pump. Look at that. That's actually holding the weight of the pump. I couldn't even pick up a piece of paper before, but you know, I couldn't even pick this up with just that tube, and now I can do this. Okay, now watch this. I'm going to put this guy on here. That's really loose. I'm just going to seal it up. Shut up. Stop it. Okay. Wait a second. Here we go. So I'm just going to seal this up here, just with a little bit of tape. Electrical tape. It's such a good sealant. It's not like, you know, it's not industrial. Actually, you can get industrial tape, electrical tape. But, I mean, you know, it is for electricity, but it does cool stuff. Kind of like duct tape does. Okay, here we go. I'm going to do that. Now, we've got this much larger area. That seal is actually really, I had a really hard time cutting that straight. I tried to get it as straight cut as I could, but I don't have a hose cutter that's that big, so I tried to use my X-Acto knife, and it was all over the place, and I couldn't pick anything up with it. I want to show you this. I can't pick anything. You'd think I'd be able to pick up this battery with this thing, but the seal totally sucks because it's not perfectly flat. So the geometry of your connection is so very important. Let me see if I can kind of cheat it. I can't even cheat it by pressing it. Anyway, here we go. What I'm going to show you is something really cool. Again, because my skin can change, and skin's a good seal, I'm going to do this. Look at that. I can really, well, that's really serious connection. Now look at this. Oh, look at that connection. That's a much better connection than I had with just this one. So what we've learned here is that area affects things a lot. The seal is so very important. It's a huge part of it. Even if we have a really small area, but we have like an excellent seal, we can pick stuff up. And we saw that with this. I was able to really kind of shake this around, but if I put it onto this, which is like huge, because it's a terrible seal, I can't even pick that up. Flow rate is important because we could see that when I was doing that with my mouth, which I had very little flow rate, I couldn't even keep this thing up in the air, because even though it's perfectly flat, the seal, the geometry between here and there, is that it's leaking. So yeah, seal is so very important. Flow rate is important, because if we have a poor seal, like I could do that. I could keep this if I just keep sucking. But as soon as I stop sucking, it falls. If that was an excellent seal, I wouldn't have to do that anymore. So I thought that was fun. Reciprocating pumps will generate the highest degree of vacuum. If you need, like scientifically, you need like a ridiculous high vacuum, then actually you can get a two-stage vacuum pump as well, just like we have a two-stage compressor. So these guys produce a lot of pressure and very little flow rate. A rotary pump can generate a high amount of flow rate with lower pressures, but sometimes that's okay, or sometimes we need that when we have a poor seal. Let's take a look at Venturi Systems. All right, so that was fun. Let's take a look at Venturi generators. So cool. Venturi generators are super cool. They actually work on pressurized air, which is weird. Let's take a look at this. So if I have pressurized air going this way and I kind of squeeze the air in here, then the air flies out here and it actually creates a vacuum in here. I mean, I'd go into Bernoulli's principle on this, which is actually cool. But we don't really need to know that. But go study that. Like, go just Google Bernoulli and vacuum vacuum Venturi generators and stuff, and see why it all works. It's actually quite amazing. It has to do with the power of the air going in and the power of the air going out has to be the same. But when you actually create a change in volume, the flow rate has to change and weird things happen. Yeah, and the pressure has to change too. And the pressure goes negative. Pretty cool. And then it sucks. All right. Yeah, totally sucks. This is the symbol for a Venturi generator, and this is how it works. We have all different kinds of Venturi generators. I don't need you guys to understand all of this type of Venturi generators. This is actually really cool. Dude, this is an inline Venturi generator. It's cool. You put pressurized air in here and vacuum comes in here. It's so unintuitive because there's this line that comes out of pressurized air and it's sucking. Cool. So yeah, just check it out. Okay, now what I want to do right now is these are Venturi generators. These are all cool and they work. This is like there's 2 and 3 and there's 1 and 2 and 3 stage Venturi generators. The three stage Venturi generators create a higher vacuum at a lower flow rate. The 1 stage Venturi generators create a higher flow rate with a lower vacuum. So depending on the application of the kind of the seal, the porosity of this thing, you want to choose a 1, a 2, or a 3. So if you really need a lot of that, or if you just need that really strong vacuum, depending on your physical connection, you'll use a different Venturi generator. Of course, if it's really leaking, then you're going to look at other options. You're going to look at a rotary generator of some type, rotary vane or something. Okay, here we go. So, dude, this is just the example here. This is kind of goes back to how vacuum actually works. It's the differential pressure between the atmosphere and the vacuum inside. So the thing that's clamping the part to your actual suction cup is the differential pressure. It's the vacuum inside and the air pressure pushing. So kind of like if you lift something up, it's kind of like the air pressure's pushing it up. Not really, but kind of. I mean, there's actually a robot or a machine or a cable or a mechanism physically doing the work to pick it up. But for it to actually hold on there, it needs to actually have enough force to actually counteract what the gravitational force is on that particular thing. So yeah, it's like the air is actually pushing the thing up in the air. It's pretty cool. Okay, so that's what's going on there. Yeah, now I want to talk about different kinds of vacuum pads depending on application. So there was an example there where there was a bellow, and the bellow has to do with if we're going to pick something up that's an odd shape. Like if I wanted to pick this up on its side because it's rounded, I'd have to use a bellow so it could like go around that. Or if I wanted to pick up a flat surface on an angle, right? So this thing was on an angle and I wanted to come down and pick it up. I could use a bellow for that. It's a pretty cool situation. So we've got all these different kinds of vacuum suction cups, and they have to do with the surface they're connecting with and what's going on. Sometimes we're picking round things up. So when we pick up a round thing, there are these different types. There's a flat, there's a ribbed flat, which is cool. A deep is for picking up round things. And a bellow, obviously it's for picking up stuff that's a weird shape and stuff like this. And then ovals. Ovals are pretty cool. I mean, we'll take a look at it. It's for picking up like little things that are actually are kind of like long shaped. And I'll show you some examples of these things. Cool. And then we also have some other things here. We've got kind of end effect size. So we've got these things, these kind of longer things that are jointable. So you can get these things so they're expandable up and down. And then you've got just really large size ones, which are pretty cool. So let's move on and take a look at this. Now, I'm gonna take a look at the sizes, and then I'm gonna go back to the sizes and shapes. And I'm gonna go back to like actually temperature variability and stuff. So now I've got some. Do I have some examples here of some different bellows? Yeah, I'm gonna go here. So this is what's going on. When we have something that's really perfectly flat and a good seal, then we use a flat pad. We can use a flat pad. Now, if it's something that is really thin, like a piece of paper, or we're picking up tin foil or something, you're going to deform it, right? So you have these things called ribbed, and they have these little ribs in here. So when you suck on it, you don't deform it. So let's just take a look at this. So if I had this guy here and then this piece of paper here, right? If I take this guy, I mean, it's a terrible seal, but if I do this and I really suck on it, I don't know if you can see, but it deformed slightly. Especially if it was a really good seal, it would really deform it. So what we want to do is we want to put this on, we want to put a ribbed on there so it doesn't deform it. If we're going to pick up something that's round, we use a deep cup, cool, kind of a deep cup. And if we're picking up something on an angle, we're going to use a bellow. And then we also have pads with spring buffers. So this is going to come down and hit here. It's going to bang onto it, suck onto it, and then it'll start to pick it up. Pretty cool situation. And then the oval pads. The oval pads are used for long, thin things like microprocessors or chips or something. ICs, integrated circuit chips. Pretty cool. Now, this is where you want the bellows, because you have this kind of deformation of your material in here. Yeah, so what you want to do is you want to use a ribbed flat pad, so it'll pick something up but it won't deform it. Pretty cool situation. Cool. So this is an example about how to choose a vacuum pad. I want to go up to like I want to talk about safety factors and material. So sometimes we're dealing with stuff that's hot. Sometimes we're dealing with stuff that's got like maybe acidic stuff on it. Maybe there's oil on there that's acidic, or maybe something that's acidic. So we have to think about the kind of material we want to make the pad out of so that we don't actually damage the pad. There are a whole bunch of different things that we need to consider here, and we have all of these different options of materials, and all of these different option materials can handle certain things. Some can handle heat, some can handle acidity, some can handle water, some can't handle water as well. So there are all these different factors here, and some don't like oil and some do like oil. So because some of the actual vacuum pads are porous themselves. So we want it to be working in a really dry environment, depending on the type of material. And also, the vacuum pad itself, the material that it's made of can be really supple, like, or it can be like really rigid. So those materials are all dependent on the application. So there's a chart here of characteristics of these materials that we can use. Let's just take a look at an example of some of these things. Okay, good. So we've got the different types. We've got this nitrate rubber, which is pretty cool. Silicone rubber, urethane rubber, floral rubber, conductive rubber, all of these other, and then we have silicone. The silicone is like, okay. You want me to change to that shape? No problem. Silicone's pretty cool. Here we go. So let's take a look at this safety factor. I need to talk to you guys about safety factors. Okay, how big do we make a vacuum cup? We want to calculate the size. We're going to go order a vacuum suction cup. How big do we make it? What's the diameter that it needs to be? And there's this whole formula here. And now we know area is this, okay? So you know how to calculate area. What I need to do is kind of think about the formula. Pressure is force. Pressure and force area. So pressure is force over area. We're going to take that formula and kind of rearrange it and just work with it. Because the pressure is the differential pressure used. So it's that negative number that we need. I'm not actually going to put it in as a negative, but we'll see it work. Okay, good. So here's this formula. Dude, if you like rearrange this formula, kind of rearrange it, the W is actually for force, but we call it weight in this case because we're picking stuff up, okay? So if you rearrange that formula, it's essentially pressure is force over area. Rearrange it and take a look at it like this. So there you go. That's the formula, and these are the dimensions. The D is the diameter of the cup, and then that calculates the area, just like the piston diameter. And then from there, you can essentially say, hey, if I have a certain weight and I'm working with a certain pressure, what diameter cup do I need? And what safety factor do I have to put into it? Yeah, safety factor. So there are two safety factors. One is just multiply whatever it is that you get by 4. So we just actually put that right in the formula. So whatever the suction cup is required, you multiply that by 4. So it's a really strong connection. Now, what if you have to pick something up like this? You pick it up like this, and you pick it up and you hold it like this, and then you move it around. Well, use a safety factor of 8. Yeah. So just keep that in mind when you're using this formula, because this T is the safety factor. Now, there's this N number, which is the number of suction cups. Now, you remember that example that I showed you earlier where there were like 6 suction cups picking up a piece of plywood? Well, I need to say, okay, if the weight of that is a certain amount and I'm using 6 suction cups, how big does each one have to be? So you can put that into the formula as well. And that's the N in the formula. Okay, good. So now we've talked about these flat pads. Dude, we're almost done. I'm just going to show you some math, and then I'm going to just show you, and then that's it. Actually, I'll just show you how to actually do the math and do some calculations. And then I'm going to show you like kind of a vacuum system as far as like the schematic goes. Here we go. So let's take a look at this. We have a substance, okay? There's something in here, okay? And what's going on is that it's got to get picked up. We're going to use a vacuum to pick it up. It's in a bath. It weighs 1 ounce. Yeah, kind of a new thing for you. It's 1/16 of a pound, okay? Weighs 1 ounce. It has a diameter of 0.6 inches. Now, what's going on is our vacuum, our suction vacuum is minus 7 psi. So it's minus 7 below atmospheric pressure. So the differential pressure is 7 psi. Okay, so we know what's going on there. Oh, right, we have some temperatures to take a look at. Dude, the part's hot. It's 110 degrees Celsius. Well, that's pretty serious, okay? So actually that should say minus 7. I apologize. Make that a minus 7 because we got minus 7 over here. So just deal with it. We have some values over here. So what we're going to do is, because it's such a hot thing, it says 120 degrees Celsius here, and it says 110 here. Okay, just deal with that too. Okay, let's move forward. Okay, no, it doesn't. Okay, sorry. If I want to choose a material, okay, I know that standard NBR rubber can handle 130, 120. It's pretty close. Silicone can handle 200. I'm thinking I probably want to go for silicone, just kind of a safety factor. Okay, so you have to make sure that one's a little bit more expensive than the other. So you may want to talk to the customer and say, well, you know what, we can go with this NBR rubber, pretty basic, it's cheap, but because it's so close, you might want to go for silicone. It'll last a little longer, but maybe they'll be like, yeah, I don't want to pay the extra $50, or sure, go for it. Okay, good. So that's what you got to do. Now you take your formula, you throw the numbers in, and you get an answer. That's actually going to give you the diameter that you need. And that's actually good. Like, that diameter is good. Even if you go a little bit lower than that or a little bit larger, you're fine. Again, even if you go a little bit lower than that diameter, you're fine, because you've got a safety factor in there of at least 4. So in this case, I've calculated a diameter of 0.213 inches. So in that case, well, a quarter inch is probably good, 0.25, because I'm not going to go find a vacuum cup of 0.213, so you use a quarter inch. So there you go, and then you'll be able to pick it up. It's pretty simple, okay? So now, I need to let you guys know about one thing before I let you go. Essentially, what we need to do is, when we're designing the valves and stuff to actuate these things, I need to design a valve that actually blows a burst of air. Wait a second, really? Yeah, because sucking something up, right? Okay, there's that vacuum sucking it up, but then I have to release it. So what I want to do is, I don't want to just stop sucking, because if it's a really good seal, it's still going to hold. So I want to stop sucking and go and blow air, and then it falls. So here we go. Let's just take a look at that. Okay, we've got my supply air in here. I have a Venturi generator. So now I've got this guy. So if I energize this, air's going to go through here. I have a silencer because they're pretty loud, because it's just blowing air out. And now I've got this vacuum coming up here. Always put some kind of filtration in there, because you're just sucking just the air into a Venturi generator. You're sucking air in there. So yeah, put a filter in there. You're picking up your part. Okay, now you want to release it. You turn the vacuum off. It could be a really good seal. So then what you do is you pulse this. This guy blows pressurized air into here. You can throttle it a little bit, so it's not like a. It's just a. It just needs to it needs to put pressurized air in there, so the vacuum is just gone. Okay. Once you do that, you're just filtering the air out here. It'll just go right out the actual vacuum pad. Now it's also, this is a pressure switch in here, and again, here you go. You're sucking air up here. You want to put any kind of place where you're sucking. You want to put some filtration in there, and you're checking your vacuum. So, dude, that's it. That's all you need to do. Just when you're sucking, you have to put that burst of air in there. So there you go. That's enough just to move forward. This introduction to vacuum systems. You guys are experts as far as introduction goes, and that's it. I don't want to talk to you anymore. Okay, bye.